which produces a quasi-crystal code or language. And that allows these geometric symbols to build up to the ordinary world of particles and forces that we see around us. So that's our program, is to model physics with a quasi-crystal code made of the simplest bit of three-dimensional information, regular tetrahedron.
And here is how our high school teacher introduced us to seeing mathematical objects. We start with a very big point, and I'm sure everybody can see it. But now there's a somewhat smaller point. Can you still see it? Come on, are you blind? Say yes. Oh, good. Phew. Much smaller point. Now, who can still see that? Raise your hand. Oh, good eyesight. All right, much smaller point, tiny point. Who can still see that one? Amazing. And now a mathematical point. Now, who can see that? Those are the true mathematicians, okay? Because it's in your mind. You know where that point is, and it's infinitely small, but you have no trouble seeing it. Now we use the same kind of mathematical seeing to go from a single point to a four-dimensional hypercube by a process called extrusion. And for that, I will have to put on my magical gloves. Now, I start out with just a mathematical point. And you know it's infinitely small, but you know where it is. It is right here. Can you see it? All right. Now, because I have these magical extrusion gloves, I can grab this point here and I can stretch it into a line. Okay? Can everybody see that mathematical line? I hope so. Now, I try to hold this line with just one hand, and here it is. Okay? And now, again, I grab that line from the top and I do my magical extrusion into a square. Everybody see that square? I hold it by a corner here. I can lay it flat onto my hand. Now again, I take my magical extrusion glove, I touch it from above, and I pull the whole square up, like that. And what do I get? A cube. You're right. So here's the cube. You can see it. I can rotate here in 3 space. Now comes the really difficult step. I want to now take this cube and extrude the whole cube into the 4th dimension. Okay, and that's a little difficult. Okay, and maybe you can understand why this is difficult by an analogy, by looking at flat land. Let's assume for the moment there's a plane, and in that plane there are these 2-dimensional worms, and they're bound to the plane. They can only move in the plane. They cannot cross each other or any objects. However, they're mathematically smart, and they know about regular polygons, even though they cannot see them the way you can see them, because they can only walk around them, measure their length of the sides, measure the various angles, make sure that all of them are the same, and then they understand what a regular polygon is, and now they can see it in their minds. But one day, a visitor comes from the 3D world and tries to explain to them what a cube is. She says, just take that square and move it upwards. No, not diagonally, really upwards, and upwards means a direction that is perpendicular to both of the edges of your square. And those flatworms, they scratch their heads and they have a hard time of really doing that. But the smarter ones, they get it and say, yeah, I can see it must be out there somewhere. Okay? So they have the same difficulties that we have when we try to see the extra dimension for the hypercube. And perhaps out there are some 4-dimensional aliens, and they're looking down on us, and they smile at our efforts of trying to point into the 4th dimension. No, that's not it. That's just diagonal in 3 dimension. But anyhow, the 4th dimension is out there. Let's go back and look at some more beautiful geometry that we can actually see it, the Platonic solids. Those 5 Platonic solids, the tetrahedron, the octahedron, the cube, the icosahedron, and the dodecahedron, have been known to mankind for more than 2 millennia. They're all totally regular polyhedra, and that means that all their faces are indistinguishable. They're all the same, all the edges are the same, and all the vertices are the same. Now, the surfaces of these objects are composed of 2-dimensional regular polygons. But in 2 dimensions, there are infinitely many of these 2-dimensional regular polygons. They go from triangles to quadrilaterals to pentagons, all the way up to infinitygons. But in 3 dimensions, there are only the 5 regular polyhedra that you see here. Now, who knows why? Who could prove that to their colleagues or maybe to their grandmother? In order to construct the surface of a Platonic solid, which is made from these 2D polygons, so that they form real physical 3D corners, you have to use at least 3 of those polygons. And then with 3 of these polygons, we can make some kind of a corner. So if we start, for instance, with just 3 squares, we can fit 3 around a joint vertex. And now we forcefully try to close this open gap. And we cannot do it in 2 dimensions. But if we allow to go in a 3rd dimension, we pop out this 3-dimensional corner. And that's a regular cube corner. And 8 of those corners make up a cube. We could also do that with starting with 3 pentagons around the joint vertex. And then we would get the dodecahedron shown at the bottom. Now we can see why there are exactly 5 Platonic solids. When we use triangles for our surface facets, we have a choice. We can either use 3 triangles forming a 3-sided pyramid, or we can 4 around the corner, or 5 around the corner. If you use 6 triangles around the corner, it gives you a flat kind of kitchen floor, okay? No longer a polygon. So we have 3 options for triangles. But when we use squares, only 3 squares work. By the time we add a 4th square, again, we have flat tiling. And with pentagons, 3 pentagons work and form the dodecahedron. Any higher n-gons are useless. Hexagons just make a flat tiling, and if you take heptagons or higher, then they don't even fit around the corner anymore. Okay, if you got that, then here is the test. Now we take a leap into the 4th dimension. We apply exactly the same kind of thinking to answer questions. How many regular Platonic polytopes are there in 4D? So how can we find out? Well, the key insight is that we need to use these regular Platonic solids to essentially make the surface or some kind of a thick crust of these 4-dimensional objects. And now we have to see how we can form 4D corners out of these 3-dimensional Platonic solids. So we took a few regular n-gons that did not quite fill the space around the vertex, and then we forced this gap to close. Now we do this 1 dimension higher. We'll take a few Platonic solids, and I'm using the same models, but now assume that this is just the front, and that basically I'm holding 3 cubes in my hand. So behind each square there's a complete 3D cube. And they all share this one edge here pointing towards you. And now I'm going to force this empty wedge of space out of existence by closing that gap. But now I cannot do that in 3 dimensions, obviously. But when I do this and I allow it to go into the 4 dimensions, something magic happens. I get a 4-dimensional corner. Now we just have to count for how many different ways we can do that given the Platonic solids, the 5 ones that we have. In this case now, the crucial value is the dihedral angle. That is the angle between 2 adjacent faces. For the cube, it would be 90 degrees. And this dihedral angle tells us how many of these objects we can fit around the common edge, and then how much empty space is left over that we can now force to close so we pop out into the 4th dimension. For a tetrahedron, that critical angle is about 70 degrees. So we can either fit 3 or 4 or 5 tetrahedra, because the sum is still less than 360 degrees around an edge. And here's now the complete analysis. With 3 tetrahedra around an edge, we get something called a simplex. 4 make the cross polytopes, 5 make the 600 cell. We have seen we take 3 cubes, that gives us the hypercube. Using 3 octahedra gives something called a 24 cell, and then using 3 dodecahedra gives a 120 cell. Now the icosahedra is kind of useless. Why? Its dihedral angle is 138, okay? Times 3 is more than 360. It's sort of like the heptagon, it's too much, you cannot fit 3 of them around a particular edge. Okay. All right, you say, well, that's nice in the abstract, but can we get the feeling of how these things actually may look?